Getting to Mars is not a rocket problem. It is a fuel problem, and specifically the problem of moving over 1,000 tons of cryogenic propellant from one spacecraft to another in zero gravity at temperatures colder than anywhere on Earth's surface without losing it, spilling it, or triggering a catastrophic pressure rupture. SpaceX built the largest rocket in history, and none of it matters until this one problem gets solved. Starship's upper stage carries approximately 1,200 metric tons of liquid oxygen and liquid methane, the propellant combination SpaceX calls methalox. Getting that upper stage off the ground requires the super heavy booster to burn through approximately 3,400 metric tons of propellant just during ascent. By the time Starship reaches low Earth orbit, the tanks are nearly empty, and an empty Starship sitting in low Earth orbit cannot reach Mars. The math simply doesn't work without refueling. The plan then is to send tanker Starships up one after another, transfer their propellant into a depot ship parked in orbit, and then fill the Mars-bound Starship from that depot. On Earth, gravity does enormous invisible work every time you move a liquid. It pulls fuel to the bottom of a tank where the outlet sits, so pumps always know where the liquid is, and pressure feeds behave predictably. Loading a rocket on a launch pad, filling a fuel truck, running a gas station, all of it depends on gravity doing that job quietly in the background. That background assistance disappears completely in orbit. Without it, propellant doesn't settle anywhere. It floats freely as blobs and distributes unpredictably throughout the entire tank volume, with liquid and gas mixing together rather than separating. A pump searching for liquid might pull in gas instead, which destroys engines and collapses transfer systems. And that's when the scale of the knowledge gap becomes clear, because as recently as July 2024, NASA's Glenn Research Center described the underlying microgravity fluid physics affecting these operations as not well understood, which means there is also no reliable way to read a fuel gauge. In zero gravity, with propellant floating in blobs and gas dispersed throughout the tank, accurately measuring how much propellant remains is its own unsolved engineering challenge, separate from the transfer problem entirely. SpaceX has been flying experimental radio frequency gauging sensors on every recent Starship flight test, specifically to build that data set, because the data doesn't yet exist. And before any of that can be addressed, there is a second, slower problem eating away at the propellant the entire time the depot sits in orbit waiting. Liquid oxygen stays liquid only below -182 degrees Celsius. Liquid methane crosses into gas above -161 degrees Celsius. Space is cold in the direction of deep shadow, but in orbit, a spacecraft cycles in and out of direct sunlight, absorbs reflected heat from Earth below, and generates thermal output from its own systems. And all of that heat bleeds continuously into the propellant tanks. The result is evaporation that never stops. SpaceX is targeting a boil-off rate below 0.1% per day, using vacuum-jacketed plumbing and multi-layer insulation throughout the vehicle. The depot and HLS variants of Starship get special-purpose insulating tiles, different from the ceramic re-entry tiles, designed to shield cryogenic propellant from solar and Earth thermal radiation during long-duration orbital storage. Starship version 3, which began flight testing in May 2026, adds 100% vacuum jacketing coverage of the header feed system and a dedicated cryogenic recirculation system for propellant management during extended coasts in space. But here's the thing. Even with all of that engineering, boil-off sits at the center of the most publicly contested number in the entire Artemis program. NASA's planning requires propellant aggregation to begin more than 200 days before crew launches, with tankers flying at a cadence of roughly one every 6 days. Boil-off accumulates across all of those days, on every tanker, on the depot itself, and the losses compound. Each day of delay in the launch cadence costs more propellant than the models originally assumed, and that is precisely why estimates of the total tanker count have varied so wildly. Elon Musk put the number at 4 to 8 tanker flights in 2021. SpaceX's vice president of customer operations said approximately 10 in 2024. The Government Accountability Office said 16 that same year as Musk. A NASA official told a congressional subcommittee the number was in the high teens in December 2023, and the NASA Office of Inspector General, writing in March 2026, deliberately declined to give any specific figure, citing the history of conflicting estimates. William Not Donordado, who spent his career at NASA working on cryogenic systems before becoming CEO of Space, one of the companies NASA contracted to develop this technology, put it plainly, you might have to launch 1 or 2 more refueling missions, and nobody really knows how many refueling missions they're going to have to do yet. That admission, from someone who knows this domain better than almost anyone, tells you something important about where the state of knowledge actually sits. And boil-off is only part of what makes the transfer itself so hard. To move propellant from one tank to another in zero gravity, the liquid first needs to reach the outlet at the bottom of the tank. And in orbit, there is no bottom. SpaceX's answer to that is a technique called settling thrust, or small reaction control system thrusters, sometimes called ullage thrusters, fire continuously before the transfer begins, providing a sustained acceleration of approximately 0.001 g, which is 1,000th of Earth's surface gravity. That tiny sustained push forces the denser liquid propellant toward the outlet end of the tank, separating it from the lighter ullage gas, and the result is a stable liquid pool at exactly the location the transfer system needs it. Once settled, the transfer runs on pressure differential rather than pumps. A pressure difference between the tanker and the receiving depot pushes propellant through the umbilical connections without any moving mechanical parts in the flow path. What sounds like the simpler part of this operation then runs into its own set of complications, beginning with a problem that hits the moment the first drop of cryogenic liquid enters the transfer line. The lines themselves are warm. The walls of the empty receiving tank are warm, and when super cold propellant contacts warm hardware, it flash evaporates on contact before it ever reaches its destination, in what engineers call parasitic losses. Notor Donato identified this as one of the factors that will only become clear once SpaceX actually runs the ship-to-ship propellant transfer in orbit. Specifically, how much propellant vaporizes on first contact with the relatively warm lines and empty tanks of the receiving vehicle. Layered on top of that is propellant stratification, where different temperature layers form inside a tank in orbit, with warmer propellant collecting near the walls and colder propellant sitting toward the center. Rapidly moving or depressurizing that thermally uneven liquid can cause warmer layers to flash boil, sending a geyser of mixed liquid and gas through the transfer lines, in a phenomenon that physically hammers valves and sensors. Managing temperature uniformity throughout the entire transfer process is what engineers describe as a subtle but genuinely critical challenge, and one that resists ground-based modeling. By the time SpaceX runs the first ship-to-ship propellant transfer in orbit, the crew will be simultaneously managing the settling problem, the chill-down problem, the stratification problem, and the gauging problem, all at once, with 2 of the largest spacecraft ever built connected by cryogenic plumbing in low Earth orbit. And before any of that begins, those 2 ships have to find each other and physically lock together.